נו,
אז איך הולך לך? הולך טוב שם, אני רואה עכשיו.
אני חושב, כן, אני מאוד מרוצה.
שמעתי מסשה שהיא בסדר.
בגולדשמיט מתי דיברת?
כן. בסדר.
שלום צביקה.
מה שלומך?
נזכרת בו.
מה זאת אומרת הזכרתי?
שכחת איך הוא נראה, לא?
אנחנו גם נפגשים היום.
נכון, ונפגשנו גם באיפה הפורטוגלי, מי זה היה?
כשהיה שר?
איזה פורטוגלי?
היה שר פורטוגלי.
זה מתחבר לעבודה של בועז ואני העבודה שלנו.
זה מתחבר, כן, כי כל הרעיון של לעבוד על מידע אלמנט התחיל מהרעיון המברק של בועז לגבי הים האדום. ומאז רק למדתי עד כמה שזה נושא שכדאי להמשיך לעבוד עליו. זה אומר שאני צריך לעמוד במקום מסוים? כי בטח זה תופס רק אוקיי, אבל זה אומר שאני צריך אז להעתיק את ה... כן, אבל היא פתוחה, צריך אני באמת פה רואים אותי הכי טוב, אני נשים את הנושא כפי זה מעבירים שיעורים
morning, everybody. Today we have Zvika Steiner. He will be our speaker. He did his undergrad and master degree in Ben Gurion University, and then he came here to do his PhD with Boaz Lazar and Jonathan Erez. And today he's doing still his, for the last 2 years or so, his postdoc at the University of Cambridge. He will talk about the major element composition of seawater as traces of processes in the ocean.
Thank you. And a major element in seawater is a subject that gained incredibly little attention in the past few decades, and the reason is the principle of constant proportions. So, in general, it was proposed in the 19th century, and it is still the main dogma in chemical oceanography, that the composition of seawater is fairly constant regardless of where we measure it, if we go to different oceans at different water depth. Meaning that we would expect that the concentrations of major elements will change only as a function of salinity, and that the ratios between major elements will be constant. However, any important biological or chemical reaction that is taking place in the ocean is actually dominated by the key role of major elements, and as long as we can quantify changes in their concentrations, we're able to more directly quantify those processes. In my talk today, I will try to answer 3 main questions. The first one is where does calcium carbonate dissolution actually take place in the North Pacific Ocean? It sounds like a trivial question, but in fact when we try to use different methods to answer it, we get profoundly different results. The second question that I will address here is whether when we use alkalinity for assessing calcium carbonate dissolution rates in the ocean, we're actually getting the right numbers or not, and if we can improve our quantification of the calcium carbonate cycle. And the third question is how can we use major element data, in particular strontium, in addition to alkalinity and calcium, to get a good quantification not only of how much calcium carbonate is precipitating or dissolving in the ocean in total, but also who is precipitating that calcium carbonate. And I will finish by saying a few words about my future plans. So, when it comes to the big question of quantifying the oceanic calcium carbonate cycle, the formation of calcium carbonate and the dissolution of calcium carbonate later, we have 3 main approaches we can take to answer such a question. The first one is to measure the production rates of calcium carbonate in the surface ocean, in the photic zone, and compare it with what we find in the deep sediments. It works very, very well when it comes to understanding the system as a whole. How does the calcium carbonate cycle works globally? But if we want to follow the effects of ocean acidification and the changes that take place within fairly short timescales, we have a problem. The productivity of calcium carbonate in the ocean is a process that is working in a timescale of days, and it changes quite rapidly, while the accumulation of material in deep sea sediments is a process that is working in a timescale of thousands of years. So we can't use it to quantify the present day processes. The next approach we can try and take is to follow the material as it's settling along the water column. And sediment traps really revolutionized our ability to follow these processes and to understand how the material is changing from the photic zone all the way down to the sediment. Here we face the issues that fluxes is actually changing the time scale of days or even hours, while logistically we can only attend a few sites for a long time series. So we can't really measure it in large enough parts of the ocean over the long term. So the practical way of quantifying changes in the calcium carbonate cycle is by following ocean chemistry, if we want to do it on large spatial scales. And the way we do it is usually using alkalinity, and we became very, very good at measuring alkalinity very, very precisely. The question is, are we measuring the right thing? And I will go to the basics of the calcium carbonate dissolution equation to ask it. So for 1 mole of calcium carbonate that is dissolved, we are neutralizing almost 1 mole of carbon dioxide. So this is a great way to neutralize carbon dioxide in the ocean and the way the ocean buffers itself on different time scales. And we have 2 products. The first is calcium. We can measure dissolved calcium directly. It's extremely challenging. We have a very high background of calcium concentrations in seawater, and we're trying to measure very small changes, so it's hard to get it precisely. The second product of this reaction are 2 moles of bicarbonate or 1 mole of carbonate, depending on the pH. We cannot measure bicarbonate or carbonate directly, but we can measure alkalinity. Total alkalinity is defined as the number of acid equivalents we need to add to 1 kilogram of seawater to reduce its pH to 4.5. So in fact it is the sum of all the weak acids and all the weak bases that we have in our water sample. And as you can see, it can contain many, many different species. It's not that bad in reality, because if we go to the surface oligotrophic ocean, the concentrations of most of these weak acids and bases is quite low, and we can simplify the equation significantly. Among these constituents, we can also claim that with for normal seawater pH, the concentrations of free hydroxyl and free hydrogen ions is very, very low, so we can usually neglect them as well. The concentrations of boron is important quantitatively, but it doesn't react much. It changes only as a function of salinity. And the concentrations of bicarbonate and carbonate change as a function of salinity, but also as a function of calcium carbonate dissolution and precipitation. So the next thing to do would be to correct everything for salinity, and it's a simple normalization to a constant salinity, and by convention, I'm using a salinity of 35. Any data that I will show from now on in this talk, regardless if it's total alkalinity or major elements, is always normalized to a constant salinity, since these processes are first, the concentrations of these elements is affected primarily by changes in salinity. If we want to use total alkalinity to quantify the calcium carbonate cycle, we have to make another important correction, and that is for the release of nutrients during the remineralization of organic matter. It is now a very routine practice to measure nitrate, phosphate, and silicate concentrations in oceanographic cruises, so we have very comprehensive data sets of that. And whenever I refer to potential alkalinity from here on in this talk, it means that I'm talking about the salinity normalized total alkalinity that is corrected for the products of organic matter respiration or remineralization. Much of the data that I will present, especially in the first half of the talk, comes from a North Pacific research expedition that I participated in last August. The cruise track was from Hawaii to Alaska, and the reason the cruise took this particular track was that it comes across some of the most corrosive waters when it comes to the calcium carbonate cycle. So the saturation state of calcite is very, very shallow in this region, and when it comes to the northern part of the North Pacific Ocean, it can be as shallow as 300 meters. The other thing that changes along this cruise, other than the expectation that calcium carbonate should dissolve at fairly shallow depth, is that we also crossed an important biogeochemical front. So we started in the center of the North Pacific subtropical gyre, and we crossed into the subpolar gyre of the North Pacific with important changes in the physical oceanography and the ecology of the system along this crossing. So this is some of the basic data that we get from such crossing. As you can see, the potential alkalinity is always lower near the surface. It is going up, and it is reaching maximum values at around 1 or 2,000 meters. Below 2,000 meters, it looks like the potential alkalinity is roughly constant in all of the oceanographic stations that we had. And we can interpret it as follows. Potential alkalinity is lower near the surface because of the uptick of alkalinity for the precipitation of calcium carbonate. Those calcium carbonate shells later settle down along the water column after the organisms that made them die. And they dissolve since they get to undersaturated waters. So we get this increase in potential alkalinity. The observation that we do not see further increase below 2,000 meters suggests that there's no more calcium carbonate dissolution below 2,000 meters, which is an odd observation because we know from sediment traps collected especially by jagoffs from the same region that about 30% of the calcium carbonate that is leaving the euphotic zone is making its way all the way to the bottom. So we should expect that a lot of calcium carbonate would dissolve. We do not find it in the sediment, and we also do not find it in the water, in the potential alkalinity data. The calcium data is a bit noisier, but it shows the same thing. We see lower value near the surface, an increase in the top 1 or 2,000 meters, and fairly stable calcium concentrations from 2,000 meters down to the bottom, given the analytical uncertainties. So again, no proof or no evidence based on the water chemistry that calcium carbonate is dissolving. So I went to the sediment and tried to see if we can find the evidence for the dissolution there. And what we did in this particular cruise is to collect short sediment cores using a multi-corer. So we get the first 30 centimeters of the mud from along those different stations with 30 centimeters roughly of the original overlaying water, the bottom waters of the North Pacific. And the first experiment was to incubate them. We took them to a cold room and let them stand while gently mixing them for a few days. It looks like the fluxes are quite noisy. You can see that we see slightly different trends, but given all the uncertainties, it's probably best to claim that the fluxes are statistically not different than zero. We were just not able to measure any flux here. When it comes to the pore waters that we separated from similar cores, we had 8 cores from each cast. Calcium concentrations very clearly decrease in those in the pore waters. It happens within the first centimeter, and it is clearly much more pronounced in the southern cores, in the cores that we collected from the subtropical jar. We don't clearly see a similar trend in the northern cores. So, and maybe it shouldn't come as such a big surprise that those sediments are not a source for calcium, given that there's no calcium to begin with. And so where does the calcium go to? The next question is if the reaction that is taking calcium is actually taking place in the first couple of centimeters, as those profiles suggest, or is it taking place deeper in the sediment? The way I try to answer it is by using calcium isotopes. So the delta calcium 44 to 40 in the pore waters is expected to go down to lower values if we have a net dissolution of calcium carbonate, and it is expected to go up to higher values if we have a net precipitation of a calcium-bearing mineral. It is not specific to calcium carbonate. We cannot distinguish calcium carbonate from other minerals. And the data is a bit noisy, the measurement error is significant, but as you can see, if any, that all of the values go up, suggesting that calcium is actively taken within the first few centimeters of those cores. And it's not only calcium that is taken there. The main elements that are taken were actually strontium and the potassium. And we have a very clear decrease in the concentrations of both of them, and we could also easily quantify it in the incubation experiments. So it looks like there's the uptake of this trio, which is quite an unusual one when it comes to mineralization. We're still not sure which mineral is actually precipitating, containing so much calcium, potassium, and strontium, but no magnesium and lithium. They didn't go down in a similar way. But it does look like, given the spread of the data and the immense size of the North Pacific Ocean, that this could actually be the reason why calcium and strontium budgets don't usually add up. It looks like we're missing a very important sink for calcium, strontium, and potassium in the deep ocean. And one of the things that I would like to do in the future is to go in more depth into the reactions that are happening there, and perhaps precipitation reactions or whatever is actually going on there. We still don't fully understand this system. So with this, I want to take you to the second question that I started my talk with, and this is how reliable are alkalinity-based estimates of the calcium carbonate cycle. So back to the potential alkalinity equation that I've shown you before. Potential alkalinity is the salinity normalized total alkalinity corrected for the respiration of organic matter. So we expect that if the assumption that we usually make when we're studying the calcium carbonate cycles, that alkalinity and calcium change as a function of the dissolution or precipitation of calcium carbonate, the formation, for alkalinity also the formation and destruction of organic matter, and for both salinity, then after correcting for salinity and organic matter, which we do by measuring those nutrients, we should get, in units of normalities or in equivalence, the exact same change in absolute values for the concentrations of calcium and potential alkalinity. So we expect calcium minus potential alkalinity to be constant anywhere in the ocean if we're not missing additional reactions. And the reason I'm questioning it and testing it is that in the late 1990s there was a series of papers by Stephanie de Villiers, and she showed that there seems to be a large excess calcium over alkalinity in the North Pacific Ocean, and attributed it to hydrothermal activity, suggesting that hydrothermal activity is an enormous flux in the North Pacific. When I do these calculations of calcium minus potential alkalinity, I actually don't find much support to the hydrothermal hypothesis in the North Pacific. The calcium and potential alkalinity data comes in fairly good agreement in the central stations. If we look to the edges, maybe it's not in such perfect agreement. So the southern station we have here, Station Aloha, the one that is very close to Hawaii, possibly, though it is within the analytical uncertainties, is showing a slight excess calcium over potential alkalinity. And one could suggest that the northern station, Station Papa, maybe shows a slight excess potential alkalinity over calcium. So the excess calcium over potential alkalinity, especially given the location near Hawaii, could come in agreement with the hydrothermal hypothesis. While the excess potential alkalinity is a bit harder to explain, it doesn't seem to come from the sediment. Another explanation would be rivers, and I will try to test this different hypothesis next. So if indeed we see a significant flux of material coming from hydrothermal activity into the North Pacific, we would expect four things to happen. The first is that the concentrations of calcium would go up. The concentrations of potential alkalinity should go down, but we also expect the concentrations of magnesium to go down, and the ratio of radiogenic strontium isotopes, so strontium-87 to strontium-86, to go down. And I tried to measure magnesium and strontium isotopes in addition to the calcium and potential alkalinity data, and I would say that given my analytical uncertainties, it seems flat. So there's no evidence for a very large flux from hydrothermal activity at this location. As for the northern station, where I suggested that the data maybe shows a slight excess alkalinity over calcium, we had a very good test for it in this cruise. We had a full oceanographic station in Resurrection Bay, which is a fjord just off the coast of Alaska, and this place receives very, very large fluxes of fresh water. It is draining an immense section of Alaska. The data from that station suggests that the concentrations of calcium and potential alkalinity increase a bit, relative to what we measure in the open North Pacific. But when it comes to calcium minus potential alkalinity, it is not very different than what we see elsewhere. So we don't see good evidence that Alaskan rivers are a major source for anomalies between calcium and potential alkalinity. And maybe it's not just for Alaska, because given, if we look at the compilation of Fry et al. Published 2 years ago, they have shown that there's no reason to think that the North Pacific rivers are a major source of alkalinity to the North Pacific in general. So the hydrothermal hypothesis doesn't seem to be the case in rivers as well in the North Pacific. And in the North Pacific, I would say that the alkalinity actually works quite well for quantifying the calcium carbonate cycle. But the same is not necessarily true in other parts of the ocean. And evidence for it comes from the Indian Ocean. In December 2015, I participated in a research expedition from Goa up here to Mauritius, which is here. And we had oceanographic stations along 67 degrees east. The data we get from the entire section suggests that, again, in units of normality, calcium and potential alkalinity changed to the exact same magnitude from the surface down to 2,000 meters, in perfect agreement. But if we look at the details, north of the equator, calcium concentrations actually increase before potential alkalinity, and potential alkalinity catch up later. So we do get an anomaly, an excess calcium anomaly, at the depth of 750 to 1,000 meters. We do not see the same south of the equator. And the oceanographic explanation for it would be that the depth of 750 to 1,000 meters in the North Indian Ocean is exactly where we expect to find the Red Sea water mass of the Indian Ocean. And we actually have new data from the Red Sea, but I will say a few words about its oceanography first. So the Red Sea is receiving surface waters coming in from the Indian Ocean and Gulf of Aden, and its only major entry point is the Straits of Bab el-Mandeb. As a vast simplification, those surface waters flow northward until they get to the North Red Sea and the Gulfs of Aqaba and Suez. The Red Sea deep waters form in winter at the northernmost part of the Red Sea basin and in the Gulfs of Aqaba and Suez. And the Red Sea water mass of the Indian Ocean is actually those deep waters that cross at deeper depth in the Straits of Bab el-Mandeb and sink to 700 or 900 meters in the Indian Ocean as they mix with Indian Ocean waters. We have surface water data from along the Red Sea, and this data was collected in December 2015, January 2016. So during the winter, when we expect mixing in the northern part of the Red Sea basin. What this data shows us is that from the Straits of Bab el-Mandeb to 24 degrees north, there's a gradual decrease in salinity normalized total alkalinity and in salinity normalized calcium concentrations. And the decrease of the two is in perfect alignment if we think that only net precipitation of calcium carbonate is the process taking place along this basin. But this changes from 24 degrees north. We still see a decrease in normalized total alkalinity, but we get an increase in calcium concentrations, and the ratio between alkalinity and calcium there is just as we would expect from a hydrothermal source. And we do not have new data from the deeper part of the Red Sea, but Erez and Krumgans collected and measured calcium and alkalinity data in a 1982 cruise, and their data shows that there's a very clear calcium to potential alkalinity anomaly, a very clear excess calcium in the deeper parts of the Red Sea. The Red Sea is a tectonically active basin, and it has hydrothermal pools, hot brines, at the deeper parts of the basin. They actually look a bit like lakes that are filling the deepest sections of that basin. And it looks like either those hydrothermal pools directly, or maybe the groundwater circulation through the Messinian gypsums that is contributing to the formation of those hot pools are making this calcium to potential alkalinity anomaly that we can trace all the way down to the equator in the North Indian Ocean. So taking into account calcium concentrations could help improve our ability to quantify the calcium carbonate cycle in that region. With this, I want to take you to a slightly different subject. So the third question that I mentioned in my introduction was whether or not we can use the major element data to not only say if calcium carbonate is dissolving, but actually or precipitating, but actually to quantify how much of the calcium carbonate is forming or dissolving in different parts of the ocean. And I will focus on the Red Sea data here, and I will I'm showing here something that I've shown before, but in a different format. So as you can see, the normalized total alkalinity of the surface waters of the Red Sea is increasing gradually as the water flow from the Straits of Bab el-Mandeb to the Gulfs of Aqaba and Suez. And this decrease, showing here 1998 data, is quite similar between the 1998 data and the 1977 data. We also have strontium data from that period from the 1998 expedition, and we can try and quantify a measure of the distribution coefficient of different elements, in this case strontium, into the calcium carbonate precipitating along this basin. So the distribution coefficient is defined as the ratio between a minor element and a major element in a solid to the ratio between the same minor element and major element in the solution from which the solid is precipitating. In our case, it's the ratio of strontium to calcium in calcium carbonate to the ratio of strontium to calcium in seawater. And it's evolving a bit along the way. And if we try to see something about the actual reactions, we would expect the distribution coefficient to equal 1 if the mineralization process is indifferent of strontium and calcium, meaning that there's no preference to the uptake of either of these elements into calcium carbonates. It should be higher than 1 if there's a preference to the uptake of strontium, and it would be lower than 1 if there's a preference to the uptake of calcium in the formation of calcium carbonates. A way to quantify this value, this distribution coefficient, over a flow track would be using the Rayleigh distillation equation. So the ratio of strontium to calcium in each of our water samples to the ratio of strontium to calcium in a reference sample equals, according to the Rayleigh distillation, to the ratio of calcium in each of our samples to the ratio of calcium in a reference sample, power the distribution coefficient minus 1. And if we will talk about the Red Sea, a natural reference sample would be water from the entry points, from the Strait of Bab el-Mandeb. We only solve the Rayleigh distillation for one value of distribution coefficient in this case, so we can only say that we are able to solve it for a system with 2 end members. And we actually have fairly good 2 end members in this case. If we can assume that we know the distribution coefficient of strontium in plankton calcium carbonate, and we know the distribution coefficient of strontium in corals, then we are able to calculate the fraction of calcium carbonate that is going into each of this type of minerals. And fortunately for us, they actually are quite different. Corals take almost an order of magnitude more strontium than plankton. So we can use it fairly well if it fits the data. As for the 1998 data, it's blended a bit, but the power of the Rayleigh distillation fit to the data was 0.64, 0.66. It is the KD minus 1, so the distribution coefficient as for 1998 along the entire Red Sea basin was 0.35 roughly, meaning that plankton had precipitated about 80% of the calcium carbonate of the Red Sea in that period, while corals contributed 20% of the total calcium carbonate. We wanted to repeat this transect because of the hypothesis that ocean acidification should decrease coral calcification rates or calcification rates in general, and we predicted that it should amount about 12 to 15% over 20 years. But it took a long time to actually get a hold of new samples, and now we have them. We have surface water samples from December 2015, April 2016, and March 2018. So a 3-year long time series, almost 20 years after this original data was collected. And this new data suggests that the total alkalinity of the Red Sea is much higher today. It starts from a similar value in the Gulf of Aden, but it is not going down as fast as it used to go down, suggesting that less alkalinity is taken for the precipitation of calcium carbonates in this basin. And again, the question is who is suffering? Who is not precipitating as much calcium carbonate? Is it the corals or is it the plankton, or a combination of the two? And going back to the Rayleigh distillation model, we find with the new data that the distribution coefficient nowadays is about 0.11, which is exactly what we would expect if all calcium carbonate is precipitated by pteropods and planktonic foraminifera, with negligible contribution by corals and probably also not important contributions by coccolith. So there is a very, very clear change in the ecology of the Red Sea. Corals are just not net accreting anymore, and this calculation is only true for the south and central Red Sea. It's not as bad in the north, I think. The question again comes to why. So 2015 and 2016 are not any random years in the study of coral reefs. These were the 2 warmest years on record, and many of the coral reefs were bleached globally, and we also have observations from the central Red Sea showing that there was mass bleaching of corals there. But as it comes to the Red Sea basin, it was suggested in the past that the Red Sea corals should survive global warming even when other reefs bleach. The reason is that the Red Sea corals thrive today with water temperatures of 31, 32 degrees Celsius, while corals worldwide bleach and usually also die at 28 degrees Celsius. 2015 was a warmer than usual year in the Red Sea, but it was only the 3rd warmest year in the last 20 years, and we did not observe such massive bleaching and mortality in the warmer 2 years. So global warming probably, or warming of this particular region, probably contributed to the death of corals, but it can't be the main cause. The other thing we thought about was ocean acidification, which was our initial prediction, but it turns out that since alkalinity increased, because of the less uptake of alkalinity for calcium carbonate formation, the saturation state of aragonite actually didn't change much. And by calculating the expected precipitation rates using the change in the aragonite saturation and the change in temperature, we only should predict about a 5 to 6% decrease, which is obviously not the case. We see a 100% decrease. We don't have actual data from that region. The problem is that because of the civil war in Yemen, no one can access the areas south of 18 degrees north. The Straits of Bab el-Mandeb are at 12.5. So we're missing a huge chunk of the Red Sea that we don't have actual data for. But I would speculate that it is probably a combination of 2 things. The first is eutrophication, due to sewage coming from the big cities that are building up along the coast of the Central and South Red Sea. And the second is probably overfishing, which could be related to the security situation in Yemen. Before I wrap up the talk, I want to say a few words about my future plans. So in the next years, I would like to keep on following 2 directions. The first is to continue the quest to quantify processes in the ocean when it comes to different cycles. And the major element seems to be a very good way of going on with that. The second is to go into more depth to the study of water-rock interactions in the context of the marine environment. So I've shown you some of the reasons that I'm interested in reverse weathering in the modern ocean. Another thing that I would like to do is to study in more depth the mechanisms for bird precipitation in the ocean. Bird is a peculiar paleoproductivity proxy. It seems to work incredibly well as a descriptor of paleoproductivity in some regions, but it doesn't work at all in others. And I think that by employing surface chemistry method, for example, by preparing monolayers of very well established and very well constrained chemistry, with a solution of relevant chemistry, we can get quite interesting info about the particular molecules that maybe bacteria or other processes contribute to this and nucleate bird at the end. I would like to say a few more words about the first two things, the strontium and the lithium cycles that I mentioned here. So I have shown you so far how the combination of strontium to calcium ratios can be used to quantify coral calcification and calcareous plankton in the Red Sea system. It doesn't work, it's not straightforward to use the same calculation if we talk about the open ocean. The reason is quite obvious. First of all, corals are of no importance in the open ocean, but there are other players in town. And when it comes to the strontium cycle, the major other player is a group of organisms called the Acantharia. They're actually quite abundant. They're radularian that precipitate strontium sulfate skeletons. And the abundance is probably the reason that at present, in the modern ocean, strontium concentrations are not constant. They are lower near the surface and they are higher below. Much of this change can probably be attributed to calcium carbonate dissolution and precipitation, but we do find several regions where it must be Acantharia or another process that we don't fully understand. We also have plankton net data from this Indian Ocean cruise and from the North Pacific that I'm not showing now, and it shows in both cases that Acantharia were actually very, very abundant where we wouldn't expect them based on the strontium chemistry profiles. So there's still something profound that we don't understand there, and it becomes important if we consider paleoceanographic reconstructions. Strontium to calcium in the shells of different organisms is a very popular proxy, mostly for temperature, but also for other processes. And even in the modern ocean, the Antarctic water masses don't form with the same strontium concentration or strontium to calcium ratio as do the North Atlantic deep waters. So there's no reason to assume that something that is controlled by circulation and ecology would behave the same in glacial periods if we don't understand it today. The other interesting major element that pops up in the ocean is lithium. So you can see here the strontium and calcium data from the surface waters of the North Pacific. You can see quite clearly, especially for strontium, the increase in concentrations, which is probably related to the upwelling of intermediate waters in the northern part of the North Pacific. Lithium behaves different. It actually peaks at 40 degrees north. It's incredibly far away from any land, and it's obviously not dominated by circulation. And I suspect that the reason for this increase is the specific location that we find it at. So this is where we transition from the subtropical gyre to the subpolar gyre, and it's a region that receives westerlies year-long, which potentially could carry dust all the way from Asia. If this hypothesis is correct, we should expect a much bigger change in surface water lithium concentrations in the Atlantic and the Mediterranean Sea. So I submitted the research proposal a couple of weeks ago, asking to go on a British ship from the UK to the Falkland Islands to test its lithium hypothesis, as well as what's actually going on with strontium in the Atlantic as the different water masses mix. So, and this is just to show you that lithium is clearly not coming from below. The deep water concentrations of lithium are lower than the surface water concentrations. So just to go back to the main line of my talk and to wrap it up, I've shown you that the water chemistry data from the North Pacific Ocean suggests that all calcium carbonate dissolution is taking place down to a depth of 1,000 or 2,000 meters, and suggests that there's no more significant dissolution flux below 2,000 meters. We know it's not the case from sediment traps, and it seems like the contact zone between the deep North Pacific sediments and the waters and the seawater of the North Pacific is a very, very active one, and we have some processes of probably precipitation of minerals that we did not expect before, that surprisingly contradicts the flux of calcium dissolution almost on a 1-to-1 ratio. We do not find any evidence for flux of calcium across this boundary. Next, I've shown you that calcium and alkalinity actually behave in a very similar way in the North Pacific, so alkalinity seems to be a very good proxy for calcium carbonate dissolution. In some particular cases, such as the Red Sea and the Red Sea water mass of the North Indian Ocean, we do need to make corrections to the alkalinity data to get good calcium carbonate dissolution estimates. And last, I've shown you how strontium data, in addition to calcium and potential alkalinity, can be used to quantify, monitor processes taking place in the ocean over a few decades, and how it allowed us to see what's going on in terms of coral reefs of the South and Central Red Sea. So before I will take questions, I have many people to thank. This list is very non-exhaustive. And the first one I would like to thank is my postdoc advisor, Sasha Turchin, and as well as my funding through a Blavatnik postdoctoral fellowship in an Isaac Newton Trust research grant. And thank you for your attention. I'd be happy to answer questions.
Just a comment for the lithium hypothesis. It's a really good idea to look at the isotopes, because the isotopes of the dust must be very, very different from the lithium isotopes in the seawater.
I know I have talked about it with some Buddha Mishra and Tipa, but it's not moving forward yet. I do hope that I will get a chance, and I think that particularly in the North Atlantic, if there is a bigger change in concentrations as I expect, the change in lithium isotopes should be very, very clear.
Any other questions?
Yes. Following this topic, I think that if indeed you're correct about your hypothesis, then dust and other markers, which, for instance, organic elements, lead, and and aluminum, that point to the first source of this dust. You can test this with adding some more elements to be measured in addition to lithium.
I agree. This particular expedition was not a geotracers one, so it's hard to show this type of data as reliable, but there was a geotracers section just a couple of months ago doing the exact same transect from Hawaii to Alaska, so I think that whatever will come out of their data should align and prove or disprove my claim about lithium.
Yeah, is there modeling the calcium profiles?
I'm sorry?
Is there modeling calcium profiles using dissolution models and flux models?
Are you asking about calcium in the sediments?
No, in this in actual oceanic profiles?
The main problem that I have with this particular data is that we don't have perfect constraints about the age of the water masses, which is something that is very, very helpful if one tries to calculate the actual flux of dissolution. We can use some older data from the same region because, for example, GeoSex provided quite a lot of carbon-14 data, and we'll try to do it, but I haven't done it yet.
Okay, let's thank Zvika again.
אני רציתי לשאול אותך, יש איזשהו קשר לסימאונס שמפוזרים בעומק הים?
אחד הדברים המרתקים שמצאנו בהפלגה הזאת זה שבכל פעם שלקחנו קורים היו המון אבנים קטנות על ראש הקורים. עכשיו אנחנו השתדלנו לעשות במקומות הכי שטוחים של הים כדי שבטוח הקורים יעבדו וגם לא חיפשנו ספציפית את הסימאונס. חלק מהאבנים שמצאנו הם בטח היו מנגניז אוקסיידס, אבל בתחנה הצפונית קיבלנו אבן שנראתה לנו בזלתית, הייתה לפחות 100 קילומטר מההר הקרוב, וכשעשיתי לה XRD מכילה, זיהינו 10 מינרלים שונים, כנראה שיש עוד כמה פאזות, לגמרי לא ברור מה היא נקראת כשאתה.
אייסראפט? לא יכול להיות אייסראפט?
אני חושב שאני נפגש עם בועז ראשון ואנחנו הולכים לאכול צהריים. תגיע אליי.
אייסראפט, יכול להיות? סתם אני זורק,
אבל
מספיק צפונה.
אין קרחונים שם.
לא, עכשיו לא, ברגע זה לא.
זה מתקשר להרצאה משבוע שעבר.
אני קצת מתקשה לחשוב על זה במרחק כל כך גדול מהחוף והיו 10,000 שנה לסדימנטים.
אתה עצמאי. אתה עצמאי, אתה יודע איפה המשרדים של האנשים האחרים.
אין בעיה, אתה יכול לעבוד, אתה לא חייב.
צביקה, ממש יופי של הרצאה, באמת. יש לי שתי צימטרים שאני מחכה, נראה לי. יוסי? אני נתקעתי לדבר שנייה אחת עם צביקה, אני מדבר... לא, תעלה, לא, אני מדבר עם בועז.
ההרצאה צריכה לקבוע את זה.
תשמע, ככה, אני מדבר על ארטק של כדי חלסיות. מה, אני לא יודע, שפתה היה לי מוצאות, פוטסיות, ארטק של פוטסיות. אני יכול להבין את הארטק של קלציום.